for our next problem, we're going to look at the integral from -1 to 2 of 1 over x squared. So first note that we could write 1 over x squared as x to the -2. And then it's easier to find the antiderivative of that. So if I add 1 to -2, I get -1, which is the same thing I divide by. So I get negative of 1 over x. Plugging in, I get -1 over 2 minus -1 over -1. Lots of negatives in there. So -1/2, and then it's going to be overall -1, which is -3/2. So this looks straightforward, but actually this is wrong. Why? Well, let's draw a picture of what's going on. This actually is a function that we should be able to draw. What this function looks like is something like that. And we're looking at the interval of -1 to 2. And so what we're trying to do here is find this area. Now first of all, note that -3/2 makes no sense at all with this picture because we'd expect to have a positive area. So what's going on here? Why can't I do this? Well, at x equals 0, we have a problem here. We have an asymptote, vertical asymptote at our x equals 0 value, or the y-axis. So let's look back at the fundamental theorem of calculus, part 2. And looking at that, let me scroll for a second. What did we miss? So it says if f is continuous on the closed interval from a to b, then the integral from a to b of f of x dx is equal to big F of b minus big F of a. So look at what we got going on here. Our function is not continuous on this interval for which we're trying to find the definite integral. So from -1 to 2, I can't use the fundamental theorem of calculus part 2. So it can't be used on the interval -1 to 2 because there's a discontinuity at x equals 0. So then this begs the question, what do I do? And the answer to that is in Calc 2. So this is a little plug for Calc 2. For now, I just wanted to illustrate that we do have to be a little bit careful here. You could take this integral on an interval that did not include x equals 0. So if I took this integral from 1 to 2, for example, on that interval, we would have no problems, and that's fine. So there could be a discontinuity somewhere on the graph. As long as you're not finding the integral that includes that discontinuity for that interval, then that's fine, but this one is not okay. So the way to deal with this is in Calc 2. So you'll have to stay tuned on this one for Calc 2. Right now, we can't do the problem. Not that we can't, but we're not going to. We have other things to do. Alright, so the last thing we're going to talk about in this section is the fundamental theorem of calculus part 1. It says if f is continuous on the closed interval from a to b, then for every x in the interval, the derivative with respect to x of the integral from a to x of f of t dt is equal to f of x. So it's easy to get bogged down in the notation here, but if you look at this sort of globally, we're taking the derivative of an integral, and we have a dummy variable t to kind of deal with the notation here in some of the particulars, and we get back to f of x. So in other words, the integral and the derivative are opposite operations, or if you take the derivative of the integral, it's going to undo it. And that shouldn't be surprising from the fundamental theorem of calculus part 2, where what we discovered is if we have a rate that we're taking the integral of, then that gets us back to the function, but specifically, the difference of that function. So here's how you could actually kind of derive this and see how the details work with the notation. So if you just look at doing this integral with the fundamental theorem of calculus part 2, the antiderivative of little f of t is big F of t, evaluated from x to a. We plug that in. If you take the derivative with respect to x of big F of x, that's our just our definition of the antiderivative, what the f prime should be. The big F prime should get you back to little f. And then the a can be anything. It can be 0 or any other constant, because when you plug in a value into the antiderivative and take the derivative of it, you just get 0. So there you can get back to the function f of x, and that's how that actually plays out with the steps in between. That's it for this section.